Hello everyone, let's look at some numericals based on Young's double slit experiment. Example 1 says, in Young's double slit experiment, the two slits are separated by 0.28 millimeter and the screen is placed 1.4 meter away. The distance between the central bright band and fourth bright band is measured to be 1.2 centimeter. Determine the wavelength of the light used. So, in this case, we need to find the wavelength of light used. If we draw the pattern of Young's double slit experiment, just the intensity pattern, then the center we get a central bright band. Let's take this as a central bright band, and then we get a dark band, the first bright band. Keep in mind that as seen in the previous classes, the intensity would decrease gradually, not like this. I'm just drawing for sake of representation of the bands. Otherwise, the pattern would be of varying intensity, not as given here. So let this be the central bright band. This would be the fourth bright band. The question says the distance between the central bright band and the fourth bright band is measured to be 1.2 centimeter. Means the distance between central bright band and this center of this is taken to be 1.2 centimeter. But this is nothing but it contains within it 4 fringes, because fringe was defined as the distance between two consecutive bright or dark band. So this is one fringe, second fringe, third and fourth fringe, which means 4 beta is equal to 1.2 into 10 power minus 2 meter. Now beta was given as lambda capital D by small d. So putting it back here, we get 4 lambda capital D by small d would be, you can write this as 12 into 10 power minus 3 meter. And if you rewrite this, the lambda is equal to, it's like 4 ones are, 4 threes are, and what remains would be just 3 into 10 power minus 3 by capital D, which is 1.4 into small d, which is 0.28 into 10 power minus 3. You can just rearrange this, write this as 3 into 10 power minus 3 into 28 into 10 power minus 5. I pulled out, this is 10 power minus 5, because I pulled out 2 here, by 14 into 10 power minus 1. So 1s are, 2s are, so it becomes 6 into 10 power minus 7, because plus 1 goes on top, same as 6000 strong. So this is the required answer for this question. Example 2 says, yellow light of wavelength 5800 angstrom from an arrow slit is incident on a double slit. If separation between the sixth bright band on one side and that on other side of the center pattern on a screen 1 meter away is 0.348 meter, then calculate the double slit separation. So the second sentence is quite lengthy, but then break it into small parts, understand it. If the separation between the sixth bright band on one side, you forget this part because it's about the screen distance, on one side and on the other side is 0.348 meter. Means if you have central bright band and suppose we have a sixth bright band somewhere on this side, the distance between these two would be 6 times beta. And also there also would be another bright band series in this direction also. So even this would be 6th bright band in the down direction. Question says if the separation between sixth bright band on one side and on the other side. So it is this separation which is given, that is given as 0.348 meter, and 1 meter is the distance between the slits and the screen. So again this would contain 6 beta. Therefore what is given is, it says 12 beta is equal to 0.348 meter. So the wavelength is given and also capital D is given. Question says find the slit separation. So 12 into beta is given as lambda d by small d, that is equal to 0.348. Now if you want to find just small d, then small d from here would be 12 into lambda is given as 5800 angstrom, which is same as, that is 5800 into 10 power minus 10 is called angstrom. That is same as 5.8 into 10 power minus 7. You can write this as 5.8 into 10 power minus 7 into 1 by 0.348. If you solve this, this will be 12 into, divide this and see, that will be equal to 16.67 into 10 power minus 7, that is equal to approximately 200 into 10 power minus 7 meter, or 20 micrometer. So this is the required answer for this question. Example 3 says, in Young's double slit experiment, if the distance between the plane of slits and the screen is increased by 10% and the slit separation is decreased by 20%, then what is the percentage change in fringe width? Recall that if you have two parameters x1 and x2, then x2 minus x1 would be the change in the parameter, x2 minus x1 by x1 would be the fractional change in parameter, multiply into 100 becomes the percentage change. So you need to find this form here. Here it is about the fringe width. So you call the fringe width as beta in the initial case, and when the distance between the slits and the screen and the distance between slits itself is changed, then beta also will change. So let's call it as beta dash. So here we need to find what is beta dash minus beta by beta. So we need to find this first. Beta is given as lambda capital D by small d, and beta dash would be equal to, lambda will not change, the same wavelength used, but the distance between the slits and the screen is changed, and also distance between the two slits has changed. It becomes lambda d dash by small d dash. Let's find what is capital D dash first. Says the distance between the plane of the slits and screen is increased by 10%, which means d dash would be d plus 10% of d. It will be d plus 10 by 100 of d, that is 0.1. Therefore d dash is equal to, it will be 1.1 into d. This is the new distance. Similarly, if you look at small d dash, it says decrease by 20%, which means this d small d dash is equal to capital D minus, it will be 0.8 times this. It is decreased by 20%, so it will be 20 by 100 into d. So this d dash will be equal to, if you solve it, becomes 0.2 d. It becomes 0.8 into d. This is what is d dash. Putting it back here, then what we get would be that b dash is equal to lambda into d dash would be 1.1 into capital D by 0.8 into small d, but this lambda capital D by small d is beta. Therefore, you can say beta dash is equal to 1.1 by 0.8 into beta. 1.1 by 0.8 is equal to 1.375. So beta dash is equal to 1.375 into beta. Now if you take minus beta dash, so beta dash minus beta, 1.375 beta minus beta, you taken minus beta on both sides, nothing has changed. This is equal to, it will be 1.375 minus 1 into beta is equal to 0.375 into beta. So what we get is, we get beta dash minus beta is equal to 0.375 into beta. If you bring beta down, then beta dash minus beta by beta is equal to 0.375. This is the fractional change, but what we want is percentage change. So in terms of percentage, we need to multiply into 100. So this change would be into 100 in terms of percentage, that is equal to 37.5%, an increase of 37.5%. So the new fringes would be 37.5 times more than the old fringes. Meaning of the answer. Example 4 says, in a double slit experiment, the distance between the slits is 3 mm and the slits are 2 meters away from the screen. Two interference patterns can be seen on the screen. One due to light of wavelength 480 nanometer, which is 480 into 10 power minus 9 meter, and other due to a wavelength 600 nanometer. What is the separation on the screen between the fifth order bright fringes of the two interference pattern? So we know that the fringe width is given as lambda d by small d, and also we know that the distance of the nth bright band is given as n lambda d by small d. Now if you use two different colors, that is use two different wavelengths, then the distance of the bright fringe also would vary because it depends on lambda. Here we need to find as to what is the separation between the fifth order of the two patterns. We need to find for the two fifth order difference patterns. That is, we need to find what is the distance of the fifth bright fringe because of the first wavelength as well as second wavelength, and find their difference because they have different separations. So in this case, what we'll do is, we'll first write the formula for any one color. So x phi for the first wavelength will be equal to, it will be phi into lambda, it will be 480 into 10 power minus 9, it's nanometer, into capital D is given as 2, that's the distance between the slit and the screen, and small d is given as 3 millimeter, so it will be 3 into 10 power minus 3 meter. You can write this as, so 5 into 2 would be 10, there's 1 power here, it becomes 10 power 2. You can write this as 48 into 10 power 2 into 10 power minus 9 by 3 into 10 power minus 3. 3 ones are 16s are is equal to 16 into 10 power minus 9 plus 2, this becomes plus 3, becomes 10 power minus 4 meter. So the distance of the fifth bright fringe because of the first wavelength is at this distance. Similarly, if we find the distance of the fifth bright fringe because of the second wavelength, that will be again same, it is 5 into, but here the wavelength is 600 nanometer. You can write that as 60 into 10 power minus 8. I'm just writing in terms of, so we can get cancelled with 3 into 2 by, this is 3 into 10 power minus 3. It's very easy from here that it's 1s are, it's 20s are. So 20 into 2 would be 40, this will be 200. 200 into 10 power minus 8 plus 3, that is 200 into 10 power minus 5 is equal to 20 into 10 power minus 4 meter. So since the wavelength is greater here, we'll have a thicker fringe so that the distance of this nth would be so much from here. That is, to understand this, this is the screen and this is the central bright band. Then just draw the center of the lines. Then for one wavelength, this is what we get. So if you look at this as 480 nanometer, this distance is 16 into 10 power minus 4 is the fifth for 480 nanometer. And then for other color, which is 600, get somewhere here. So this distance be 20 into 10 power minus 4. It's again the fifth bright band because of 600 nanometer. We want this difference, which basically is nothing but difference of these values. Mathematically, you can say that just x phi or some random notation is equal to x phi for second color minus x of fifth for the first color, and that is equal to this 20 into 10 power minus 4 minus 16 into 10 power minus 4, that is equal to 4 into 10 power minus 4 meter. This is the required answer. Example 5 says, in a double slit experiment, sodium light of wavelength 589 nanometer produces fringes spaced 1.8 millimeter on a screen. See, in sometimes questions, the words fringes and bands are interchanged. Don't get confused here, because some textbooks or some books will write bands as fringes and vice versa. So don't get confused. The wavelength of sodium light is given as 589 nanometer. Produces fringes spaced 1.8 millimeter on a screen. If the source is replaced by another of wavelength 436 nanometer, then find the fringe spacing. So here we need to find the fringe spacing. So beta is given as lambda d by small d. We need to find the fringe spacing when we have different wavelength. So in the first case, when the wavelength is 589 nanometer, in that case the fringe width is 1.8 millimeter. And when you replace it by different wavelength, what is the fringe width? Now in this case, capital D and small d remain same. Only the light wavelength is changed. So from here you can say that beta, say beta 2 by beta 1. We divide them, it becomes lambda 2 by lambda 1. The lambda 2 would be this color. So it becomes 436 into 10 power minus 9 by 589 into 10 power minus 9. And if you cancel this and solve and see this, that's equal to 0.740. Beta 2 is equal to 0.740 into beta 1. But beta 1 is the fringe width corresponding to the first wavelength, which means the first wavelength is taken in this case as 589 nanometer, and the corresponding distance what? 1.8 millimeter. So it is this 0.740 into 1.8 millimeter. So into 1.8 into 10 power minus 3 meter, that is equal to 1.33. So this is the answer.